Okay. All right. Class, we are starting 2.5. We called vectors and not like mathematical vectors, not this vector. That's a different vector. And so, even though Piranagon was pretty cool, though, gotta say, if it worked, though, that's the thing. Eh. All right. So, vector is what is it? Is an array. It's an arrow that represents magnitude and direction. So, if you have something like this it represents 50 miles per hour, so like a wind or something like that, right? Wind is going 50 miles per hour due south, exactly due south. Hey, that's right. Remember how we talked about bearings as well? Bearings might go into this today as well. All right. So if that arrow is half as long, then we have ourselves 25 miles per hour due south. We good? Direction is still the same, just how fast something is going is not. And then if I flip the direction, again, notice the size of the arrow is still the same. So it's still 25 miles per hour, but it's now due north. Just the direction has changed. We're good. Jamming. Here's notation for it. So vectors, they are represented by capital letters and they are always bold. So a bold capital V represents vector. A bold capital V with an arrow on top of it is still a vector. And then if you want to go through starting at point A and it goes through exactly point B, then we have AB, but then the arrow still goes through point B. We're good? All right, a scalar. Scalar now is a lowercase letter or bar, bars representing the vector. So just that one right there. So sometimes they say, hey, the magnitude is X, or you could say X is equal to this, and we know that's magnitude. Well, or then we have this guy. We use it for absolute values. So if you stick numbers in here, it's absolute value. If you stick variables in here, it's absolute value. If you stick a vector in here, it's magnitude. Cool. So same symbol, different context means a totally different thing. Jamming. Okay. So what we're going to do today is we're going to do a geometric approach to vectors. Later on in the course, we'll do an algebraic approach. So we're going to visually try to see it. We good? So first things first is what it means to have two vectors that are equal to each other. Vectors that are equal, they have to have the same length or magnitude, and they have to have the exact same direction. Therefore, we know that you have, if any one of those are off, all right, so then how do we say two vectors are equal to each other? We just say this, that V1 is equal to V2. So those look the same. They have the same direction. They have the same magnitude. They're not in the same space. That's okay, as long as they have the same direction. They're going the same direction, and they're going as fast the same direction. So V3 is not the same. True, true. So let's do this one right here. We'll just this. V1 does not equal V3, meaning V1 is not the same as V3. And then V2 is not the same as V3. Okay, are we good there? Chairman? And then one more thing. So equality of vectors and something called the zero vector. Eventually we get something called a zero vector. It just means that there's no magnitude. And because there's no magnitude, it's really not going any direction either. So it just stops. So things that are actually stationary, we technically they end in a zero vector. You guys are not falling through the earth right now. True. So that means the gravity pushing down on you, right? And the floor that we are standing on, they equal each other out. We good? So that means we're not flying through the air nor going through the floor. Cool. Okay, so let's take a look at some. So it's not like all theoretical stuff. So, boom. Are we good there? Just driving a car. How many forces or how many vectors are pushing at you? We're not even talking about you sitting in the car, just a car itself, right? So think about a car itself. We have the weight of the car right here pulling down due to gravity. We also have called the reaction force because it's not going through the street, right? It's not lifting up in the air. So the green and the blue right here, they must be equal to each other at that point. We good? Jam. And then we got the other stuff here. So driving force, if it's going forward. Then we have friction, which is the tires hitting the floor, right? There's a force there as well. And then air resistance. So when you're driving a car forward, really you have the gas and the engine of the car driving it forward, and you have two things pushing it back. Air hitting the car and the amount of friction that the tires are having with the road. Are we good? All those are forces. 1, 2, 3, 4, 5. 5 vectors are really operating when you're driving a car. Next, airplane. There's 4 forces because it's really not touching the ground. So thrust is kind of going forward. We have something called drag or air resistance technically. And you eliminate the most amount of drag on an airplane by making it tubular. We're good? By making the wings a certain direction or a certain way. All that is just to eliminate drag as much as possible. Then we have something called lift. And then we have something called the weight of the airplane itself. I find it always so fascinating. Like how much does an airplane weigh and it just glides through the air? Isn't that just craziness? Yeah.
Did you know it's more of like a single engine aircraft, but the thrust is actually at an angle to one side because of the forces of the engine and the vibrations from it. So it'll push the aircraft along a different way technically with the thrust. So you have to counteract it. Like
Interesting.
An example is this one aircraft, the Cessna 120.
Mm-hmm.
The engine produces so much vibration that it just pushes the aircraft nose towards your left. And so you have to apply controls to push it back to the right to stay going straight.
Interesting. Okay, cool. And it's just as if it's a single engine airplane, the prop engine?
Yeah,
so it's sitting in front, right?
It changes where the thrust is going exactly because there's so much weight going in one direction.
Oh, for sure. Yeah, gotcha. Yeah, that makes sense.
A lot of large aircraft counteract this by having their engines
on both sides,
props in different directions. Mm-hmm. Like a lot of jets have their jet turbines turn in different directions. And stuff like that.
Sure, yeah. So you have one turbine spinning this way, right? Mm-hmm. But because of that, you're going to have a little bit of force pulling you this way. Yeah, so you have the other engine pulling this way. So then you have two engines pulling different directions so that the force is counteracted.
Which is why on some passenger liners, if an engine goes out, they have to fully trim out the rudder.
The other one. Mm-hmm. Or compensate with rudder. Yeah. Yeah, it is crazy. Kind of fun stuff there. Okay, and then the other one is just this right here, a box sitting, called a cardboard box. We have something called gravity pushing down on it. The normal force, notice the normal force is just straight up from the box. Then it's still sitting on something, so there's a friction right here. And then there's external force, whatever that is, pushing down on it. And then there's the angle. Kind of crazy. Have you seen that in physics? Yes.
Mine.
Drama or okay?
Although that's not a box, it's a car. It's a very beautifully illustrated car.
Yeah. All right, guys, let's go there. So addition and subtraction. So did you guys do vectors already in physics?
Right.
Okay, cool. Okay, awesome. And so trigonometry, the way I introduce it is probably a little bit different than this bear introducing it because, again, we're coming from two different, understandings of it as well, right? But ultimately, it's a cool thing. All right, so how do we add and subtract vectors? Do you guys know that?
Triangle.
Triangle, okay. Yeah, we'll get to triangle here. But just adding the vectors together. If you say wind is going this way, or as Gavin was saying, let's say the wind on the airplane is pushing it this way. We're good? And then you also have the airplane going forward as well, right? So then how do we add things together? We add them, we just say toe to nose. We good? If you're going to add these guys together, U and V, notice that's the UV vector, right? This guy just got translated from here to here. But I want to add these together. I want to know what's the combined force. If I am, this would be good, a ship, right? A ship at sea is going this way. We're good? But then the waves are hitting the ship here. So am I really going straight? No, I'm kind of going like that direction, right? Because the wind is, as the wind and the waves hit me, I'm technically off, even though my directional compass and everything says I'm going this way. We're good. So it's called true direction. So how do we do this? How do we add? Bless you, bless you. So U is the boat itself going. V is the direction of the wind hitting the boat. We good? So now the question is, what's the true speed or where direction of the boat? It's this right here. We connect, we saw them head to toes. So then, and so on right triangles, because you guys, right? So triangle, if it's a right triangle, that's great, right? But most of the time it's not right triangles, right? It's going to be, now today we're going to deal with just right triangles because that's all we know. When we get to chapter 7, we get to move off of the right triangle and use aiming angles at that point. Okay, so how do we add two vectors together? It's always head to toe until we get our addition of all of them. We're good? So now this way right here. So if this makes sense, this is the boat going in the ocean. The V is the wind hitting the boat. So really the true direction of the boat is this right here. We're good? So even though the compass on the boat says we're going this way, really we're going this way.
So, well, what did you actually be doing?
It's good. So, or no, we good?
Yeah.
Okay.
We have to think about the fact that when we look at this, we're thinking in a triangle, U, V, or U plus V, if you add the sides, it's gonna be too long, right? Like, is that what you're thinking? Okay. It's really because the V is gonna be negative, right?
Correct. Yeah, because knees, yeah, it goes in a southern direction. U is going in a northern direction. All right, so then we have to almost like we have to slide this guy. We have to slide it right to the end of this right here. So we have to connect arrow to start, or we say head to toe of the next one. Okay, so then the question is if I add two arrows, so, and does that make sense about the boat in the ocean? Is that right? The compass and everything else says we're going this direction. The wind is hitting the boat. So our true direction is this one. So boats always have to compensate. I know arrow goes this way. I know the arrow. So then let's calculate whatever my true direction is, which is a lot different. Okay, that's adding. How about if we do subtraction? I want to subtract these guys. If I want to go subtract, all I do is I flip the arrow on itself. Weird. We good there? All we do is to go negative, we just flip the arrow. So V was going southern direction, now it's going northern direction, and now let's subtract these two. So here it is. Here's U again. True? But the negative V is and they flipped, so it's like right here now. Are we good there? So that's U, and then the connection, that's negative V. So now that's what we have. Too weird. So there's addition and subtraction of these guys. We are mostly going to do addition though. We don't really do subtraction. We don't like say, you know what? If the wind was not here, what direction would we go? Or if the wind was going the exact opposite direction, where would we be at? Like that makes no sense with it. Okay, but let's do some problems here that would actually make sense with this. Now, we are going to form right triangles. So the whole point is like, hey, where's a right triangle that you can form? We good? Cool. So here it is. Abel, you're here now. Well, Abel is in the textbook, at least in the PowerPoints now. Abel, did you know, is on a boat and is crossing the river that runs due south. The boat is pointed due east and is moving through the water at 10 miles an hour. And if the current of the boat is constant at 5 miles per hour, find the actual course of the boat that Abel is going through the water to. So he's trying to cross a river. And in crossing the river, you got the river flow going down. So the question is, now in California, we don't think about that stuff. I have a friend that used to work on the Mississippi River, and they used to calculate this all the time. Because Mississippi River is wide, sometimes 1 or 2 miles wide. So from them to get to one side to the other, they have to compensate for it because the river's just flowing. And if they need to go down, which is kind of the fun part, they said if you start from this side, well, let's go for you guys here. Start from this side, and you have to go down to this. We use hardly any gas. We actually can just cruise down the river, right? And then we get to where we need to get to, right? To go up, we got to use a whole bunch of gas to get up. Why? Because you're going against the river flow, right? To get actually where you need to get to, right? The California, not as much of a problem as some other places. Okay, let's jam. Let's go with it. So able crossing boat, let's draw this out. So we got one side of the river. We got the other side of the river. And we got the water flowing in the river. We good? Where does he start out from? He is headed due east, so he's going from here, east-west. He's pointed due east, okay? Moving through the water, so I'm going to go like this. Here's my 10 miles an hour, is that right? So make it about-ish, right? So that's going to be my 10. If the current of the river is constant, 5 miles per hour, and which way is it going? Does it say which? Oh, yeah, over here. It says the river that runs due south. So if I'm going to do 5 miles an hour, that arrow has to be to the south, and then how long? About half the distance of whatever that is. That's 10 miles per hour. If we can label it if we need to, that's going to be 5 miles per hour. So then that's what we're looking for. We're good? That's probably what you guys did in physics. Is that right?
I know just metric.
Mm-hmm.
Newtons.
So I need magnitude and I need direction. That's what I need. So magnitude is pretty easy because I can see that is a right triangle. Is that right? So what we would do is this. Let's just hone in on the triangle itself that has just been formed, right? So everybody see the right triangle? Let's draw it out off to the side, not inside our little, off to the side. Magnitude, there it is. I didn't draw it off the side. Okay, you guys are good with magnitude. It's 10 squared plus 5 squared. Bless you. And that's going to be 100 plus 25, so 125, so square root of 125. If you can do that calculator, it's fine. If you want to break it down to the exact answer, which is 5 root 5, but essentially it's going to be the C value. Why did I get the C value? Whoa. Okay. So what's happening. Did it just go this direction on Marsh? Okay. I thought that'd be crazy. Oh, yes, I'll have the glare is there. Thank you so much for the reminder. Please remind me. I don't think about the glare because I'm not looking at it from that angle. Trigonometry angle.
What angle was the worst?
So are we good there? So real quick here, what is this on the calculator? 5 times root 5 or square root 25? About-ish. Sweet. Okay, good there. All right, so now let's take a look at the angle itself. Every good, we formed that right triangle right there. We need to figure out the angle. That's 10, that's 5, it's a right triangle, and I have myself theta. Oh, went ahead of myself here. Which trig function should I use? Tangent it is. Tangent of, and I got to use theta here, so theta is equal to 5 over 10. Hey, that 1/2 again shows up, is that right? So it is tangent inverse of 5 over 10 or 0.5 or a 1/2.
What is that?
Mm-hmm. 26.6, 26.7-ish, somewhere. Degree symbol there. Cool, okay. Based upon that, here's what we got to do. Now we have to write down. Oh, do you guys remember? For the bearing, remember for the bearing, if we do the bearing stuff, we have to write it down like this. Yeah, we got to go like this, right? This is my, whoa, that's really bad. This should be, that's north and south, is that right? This right here is west and east. So our bearing always comes from our north or south line only. So in this case, it's this angle here. What is this angle right here? 63.4. Are we good? So that means it is south, 63.4 degrees east. We good? So we measure, we take the north or south. And this guy is, anybody got this one on a calculator?
11.18.
Okay, 11.18. I think I put 11.2, but close enough here. And that is in terms of miles per hour. Is that right? Cool. Okay. Are we good? 11.2, 11.18. Does Miss Bear really think about significant digits though?
Oh my goodness.
Science teachers.
I don't know.
That's the Sig Figs. Uh-huh. Gotcha.
Like,
All right, let's go with it here. So let's see if this makes sense. And finally, Abel, did you know, Abel, that you are heading south 63.4 degrees east at 11.18 miles per hour, 11.2.
so it's able. Able here is the vector. They say is folded and this.
It has to be a letter only, though. So if it was just an A, it would, yeah. Okay, are we good there? So you guys talk to me. How is this different from physics? Any difference from physics, or the pretty much the same?
It's recent.
Yeah, okay. All right, let's jam to the next one here. And doom doom.
You used to be human, right?
Yeah, Lucas is having fun. Lucas, did I show you the human cannonball video? Did we do that last?
Do that.
Oh, I gotta find it. Okay, let's see if we can find it. Okay.
And so.
All right, guys, all yours for this one. You should be able to get it. Let's see. Lucas shot as a human cannonball with initial velocity of 67 miles per hour at an angle of 60 degrees. I need you guys to find the magnitudes. Oh, wow. Okay, so, whoa. Okay, multiple things here. I need to find the magnitudes of the horizontal and the vertical vector components. Whoa, that's great.
Do you know which means well?
So we need to know how fast it is going up. And I also need to know how fast is he going sideways. That's the thing. I need to know both of those. So
Should we calculate for graph?
I got to give you some. I got to give you some formulas since we're doing components now, right? So the formulas before we get there.
Yeah.
So let's do the formulas here. But let's draw it out. If this makes sense. Is that the drawing out of it? Yeah. All right. So now the question is this: if you look at this, well, I need to know the blue. Here it is. I need to know the magnitude of this right here. Actually, no, let's see which one is the first one. Yeah, horizontal. I need to know the magnitude of this blue line. Notice it's kind of connected right on top, close there. What's the magnitude of that blue line? I'm going to horizontal.
67 times sine 60.
Oh, cool. It's just a trig function. Is that right? How do you get adjacent side?
It's 30 cut.
Sine
Cosine. Absolutely. So really, we have this set up. Cosine of 60 degrees is equal to, now I've got to label it. I'm going to label it as x. Adjacent over hypotenuse, which is 67. We're good? So 67 cosine of 60 degrees is equal to x. Or we can call it like this. So let's call it officially here. Can we do this one? We're going to call it V, capital V, and we're going to do, just underneath it, we're going to write a little x next to it. So it's the velocity how fast something is going. So I'm gonna rewrite this one here as just v of x. All right, what is v of x? 33.5 miles per hour. Perfect. Okay, then let's go the other way. So now notice real quick here. If I'm trying to figure out this part right here, is this the same length as this right here? Are these guys both the same? Yeah. So really, I'm just making another triangle right here. That's all. It's a right triangle. So what gives me opposite and hypotenuse connection? Sine. So sine of 60 degrees is equal to y. I'll put y over here. Oh, v of y, since we're dealing with vectors, over 67, or 67 sine of 60 equals v of y. And then anybody calculated v of y yet? 58 miles per hour. So he is going up. Stir right, then he's going horizontally. We're good. Sweet. Okay.
Now we have to find out what is speed, slow, and power.
Oh, that's true. So here's the thing with. Do you guys know the formula?
It's what we have. Oh no! Wait a minute. It's which one do you want to do? So we have the initial velocity. And
So there's a formula to say like eventually he's going to come down, right? So there's a formula to include gravity in it as well, right? So he's going up 58 feet per second, right? 50 feet per second, miles per hour, right? And then as he gets to the top, he's going to maximize, right? He's going to come down. So there's a formula for that arc that we have to do.
we're trying to find out how long it takes to stand still.
Ooh, then if you put the time factor into it, which is now a totally different thing as
And
well.
what about airs?
And then air resistance, because that has to be compensated. And then and then as he flies, as Lucas flies, he can fly like this, which is to minimize air resistance, right? As much as possible. But if he spreads out like this, then he's maximizing air resistance.
Actually, to minimize the air resistance, then like.
Okay. So while Will is doing that, we're going to move on to the next one. We're good? So now we have human and cannonball. Thank you, Lucas, so much for doing that one. So we have this now. Hey, Lila's in here now too. They're all here. Lila shoots an arrow. I don't know. Do you shoot arrows, Lila? First of all,
We've got it.
ever shot an arrow? Did you ever shot an arrow?
Okay, I probably.
Forgot an extra O in there. So Lila shots an arrow into the air. So that horizontal velocity is 30 feet per second. Vertical velocity is 20 feet per second. Oh, interesting. Okay, so now we go the other way. I know how fast it's going horizontally. I know how fast it's going vertically. Now the question is, can you give me the velocity of the arrow itself? So this is the exact opposite direction of what we did with Lucas. All right. Give me the give me the velocity of there, and then also give me the angle itself, right? The angle of it. And did you guys have to deal with force as well? Did you guys do force? Interesting. Okay. And is this helping understand the physics part? Okay. So here's Lila. As she shots the arrow, it goes like this initially, right? We know this way it's 30 feet per second. This way it is 20 feet per second. Can we make a little triangle out of this? Yes. Make a right triangle. Absolutely. We just need to put this 20 right over here. 20 actually needs to be scooted. Oh, notice we're doing exactly the same thing, right? We're scooting it, keeping the same exact magnitude, keeping the same direction, right? We're scooting it right over here. And then that forms a right triangle. Now the 20 is over here. So how do we find the magnitude? Pythagorean theorem. Absolutely. Go for it, guys. Give me Pythagorean theorem based upon this. 900 plus, is it plus 400? Is that right?
Yes.
Plus 400, which is 1300? And is that actually...
36.0555.
Oh, okay, just right about 36. Okay, 36 feet per second. That's how fast the arrow is going. That's the magnitude. Now the question is, what is my angle? Now this one, because when you shoot an arrow, you're not looking at like how much north, how much south, right? Because you're not like dealing with the globe. So at this point, I just need to know angle of elevation. What is the angle of elevation? That's what I... Trig function. Tangent, of course. Tangent theta is equal to opposite over adjacent, which makes it to be theta equals to tangent inverse of 20 over 30. And if you put tangent inverse of 2/3, would you still get the same answer? Chips. And what is the angle of elevation? Okay, so I'm going to 33.7 degrees. Okay, how do we write this out? Because initially, there's no x's in here, is that right? So we do have to write this out in a sentence in English of how this works here. So I would say this. Let me do it the fast way. Ready? Whoa, that was fast way. So here, so the arrow is shot at 36 feet per second with an angle of elevation of 33.7 degrees. Are we good? So Jam, okay, that is a vector. We good? And we did an easy one example. We did one with bearings, and we need to find components. Then we did one with components. We actually had to find the bearing. We good? So we went backwards here. So where are these vectors used at? Is when we deal with force. True. Whoa, too fast here. Wee. So I went a little. What? Okay. There we go. So, okay. So anytime we do, so we talked about it, right? The car driving through, right? There's 5 forces acting on the car. Airplane flying through the air. There's 4 forces acting on the airplane. Cool. So force, here it is. Loosely defined is anything that's pushing or pulling the object. We good? So right now, as we're sitting, right, we have gravity pushing on us. Is that right? If someone pulls on you, that means it puts a pull force on you, right? So we can either push a car, right? Or we can actually pull a car, depending on what you want to do. And those tough man ones where they actually start pushing or pulling an airplane. Yes. No tough man challenge. Have you guys ever seen those before?
Yeah, but not an airplane.
An airplane?
Oh,
I heard of a man who ate an airplane.
Ate an airplane.
Yeah.
A chocolate airplane about this big?
No. Ate an entire airplane.
What do you mean? Like
He-
metal? He
had
actually ate
really
metal.
strong digestive acids, and he could dissolve light metal alloys. So he ate an airplane.
This is worse than.
Dang, okay.
Yeah, just
That gets me a stomachache already here. Just thinking
yeah.
about it.
He like ate metal since like the age of 7,
Wow.
and he eventually worked up to eating an airplane. He was in the Guinness World Book of World Records.
Oh, wow. That is crazy. That is crazy.
Most airplanes wouldn't.
All right, let's go with it. Let's not eat anything, but let's go take a look at this here. So this thing just says this. If you are stationary, you guys are stationary, all the forces acting upon you should be equal to 0 at that point, right? So we'll see what we do with that here. And here it is. This one I just used the ones in the book. So this is from the textbook. It says Benny is 5 years old and weighs 50 pounds. He is sitting on a swing when his sister Stacy pulls him and the swing back horizontally through an angle of 30 degrees and then stops. Here it is. I needed to find the tension on the ropes of the swing, that little T value, and the magnitude of the force exerted by Stacy. Figure 17 diagram is shown below. So notice we have a few things, right? Can we just draw the forces as they are at this point? Can we draw the forces as they are? So that T value is over there, is that right? And then here's the tricky part. And then afterwards, we're going to try to convert this to a right angle. Good. So let's see. So are we okay with the T force there, right? T force is coming out. I'm not going to worry about the degree measurement right now. We'll deal with that a little bit later. H is going horizontal, and then the weight of Benny is going down. Good. So you should redraw it just like this, right? We're good. Cool. Okay. So here it is. Because Stacy has not let go of Benny yet, Benny is stationary, right? So that means at this point, we should be able to make a triangle out of these. And in this case, it's set up as a right triangle. So can I move these forces around somehow so they make a right triangle? And you can move them 3 different ways. We good? Just so you know, I'm going to move them one of the 3 ways. Let's see if we can kind of do this here. I'm going to go like this. I'm going to say, that little T value, I'm going to leave the same. We good? This little H one, I'm going to just slide it back. We good? Let's slide it back over here. So this is H now. Good there? Doesn't look the same just because I didn't draw it very well. So the T, I stayed in one spot. This little H right here, H, I scooted it this way. Now, I was not drawing it correctly here. So, everybody okay there?
Mm-hmm.
And then this little W vector came over here, and then I slid this up. So because Benny's stationary, those should all work out. We good? Now, the only other thing is that little angle. Yeah, 30 degrees. So let's do this again just to make sure we got it here. Good? And let's draw out that little 30-degree angle. So let me go back real quick here to the problem because I know it kind of makes sense if we do it. So I'm going to write it out. Let's see. Let's see. Yeah. So this little H right here went to here. Everybody okay with H being here? And this little W went here and then moved up. So now the question is, where did the 30-degree angle come from? Because that always is a trouble. Notice if Benny was on the swing and Stacy did not pull him back, this would be the 30-degree angle. Is that right? And notice these two are parallel to each other. Is that right? So it is similar triangles. That's how we get the 30-degree. Good. So it's not the exact same 30-degree angles there, but it's similar triangles. Okay, let's jam from here. Now we can figure out what we need is we need the tension on T and the tension on H. That's what we want. We know W is 50 because he's 50 pounds. So let's jam. Let's draw it out now. That is W is, or the magnitude of W is 50. Everybody agree there? And since I know that, I can figure out the rest. Is that true? See if you guys can. Cosine of 30 degrees is magnitude of Benny's weight and the tension. And I know what that is. That is 50 on top and magnitude of T is on the bottom. How do we find the answer there? And T is going to be 50 divided by cosine of 30. Are we okay with that? I switched those two around. And I got myself 57.71. Oh, sorry, 7.7 pounds. It's a LB with a dot next to it because that's how much force is being applied. Okay, and then the other one is how do we figure out what we need? What we need? We know this to be 50, right? That's 50, right? We know that. We just figured out the magnitude of T. So on that rope, right? On that rope that's hanging from Benny, it's 57.7 pounds. Why is that important? It is because ropes on swings better be able to hold 57.7 pounds, right? For Benny, or else he's in trouble. Okay, how do we figure out h? Which trig function will give us h from w?
Square root of 3.
True, yeah, it's a 30, 60, 90 triangle, right? If we want to do that, but which trig function will help us though if we do any trig functions? See again? Any of them. I want to go from W and I want to get to H.
Yeah.
Tangent would probably be the best one to use, right? Because it's a given value. So tangent, 30 degrees is magnitude of H over magnitude of W, which we know W to be 50. So tangent of 30 degrees is magnitude of H over 50, multiplied by 50 on both sides. And anybody got magnitude of H? So this is
20.675.
perfect. Okay, 20. I got 9, but it could be, I could be doing it. You can do it on your calculator just to make sure I got it right. It's okay. 8, 6 to 9. Okay, gotcha. Just want to make sure. All right, that is it, guys. We good? So that is force. Sometimes given in pounds, sometimes given in newtons, depends on what you want. And then we got one more problem. So that is force. The other one that vectors are used in is something called work. How much work is done. And so there it is. If you want to write down the formula, we're just going to plug in the formula. The work, how much work is done is the force that's being applied, the angle of that force, and then the distance that it has to carry. So if you carry 20 pounds, 2 miles, right? That is less work than carrying something 24 miles, right? There's more work involved. So it has a little distance component. All right, tell me if that makes sense there with the formula. Let's plug in. So here's Mr. G. Mr. G. Mr. G is pulling 2 elementary school kids in a wagon at a force of 25 pounds on the handle and at an angle of 30 degrees with a horizontal. How much work is going to be done if he pulls them 350 feet? So then you can just tell your parents, like, you know, I always do work. All right, now let's see. You guys figured that one out. And it's just based on the formula. So find out what is the F force, find out what the angle is, and you can use cosine, right? You're just jumping between this formula right here. And I think you have all the components of that formula. Do you know what the force is? How many pounds? Do you know the angle of elevation to the horizontal with cosine? And then do you know how many feet he actually dragged? Or now we're not looking at friction of the cart too, right? We're not looking at any of that other stuff though, right? So all you're there. While you guys are doing that, check with the person next to you. I'm going to try to find, can I slide? Everybody got all the numbers? Yep. Formula. Work equals magnitude of F, cosine theta, all that multiplied by D, or the distance that Mr. G had to pour on him. Cool. All right. We good. We're jamming. Okay. We have like 3 more minutes. Is that right? I think. Yeah. Okay. As you guys are doing that, we good? Just try yourself. It's going to be plug into the formula only, right? I'm going to try to find the video.
250.
350.
350?
And you guys can give me the answer that you get. I'll say yes or no.
I only have the formula. I only have.
There's 25. It's 25 and 30.
Why don't I have it? I'm not sure why I don't have it.
Let's draw the right. Does anyone know how far you went? Part of the given question.
All right, and we go 2 minutes to go. Here it is. Roomp. 25 pounds. Angle is 30 degrees. And we plug everything in. Are we good? So how about 25 times cosine of 30 degrees times 350 feet? Are we good there? Anybody got an answer yet? Perfect. Yeah. So, um, because of sig figs, they just put it as 7,600. You have two sig figs because of the 3,300. Okay. Half a minute. We good? Human cannonball, half a minute video. Sure. Let's go with. All right. Here it is. Oh, that's close. He was at the end of that netting. Some physicists did not do that. Totally correct here. There it is. All right. You guys are out of here. See you guys on Monday. I'm glad the bike's still coming on. Just in case if I miss a minute. Well, that's the one that just. I'll come check it out. Thank you. See you guys. Yep, absolutely.
Okay. It's like this guy for high campus. And you think that there's somebody jumping alongside him. So there's a lot of times somebody like dropping us alongside. Uh-huh. They call it the water. Oh. So it's falling. It's pretty blowing up like animals around it, in fact. Yeah. Sometimes I do is like random three followers shot. That is a cameraman. You look good. You know. You're
Only short. But laughing
Stuff. That is so cool. What are you guys filming?
every day.
Yeah. Oh, awesome. Hi, Lucianne. How are you? Yes, Miss Bell.
So off.
Should we call you Cleopatra?
Oh no. It's I think it's half of the night on the night. Oh, that was funny. Yeah, so it disappeared. It disappeared. Yeah, yeah. I'll tell you what the we have. Is there a beer? Here. So there's one here. You want to sitting on a chair?
Yeah, you are.
Yeah. The right hand spot. Oh, I play here. Okay, this is how it's gonna go when I put it in. Okay.